Yeah, I mean, just like if you recreate it. Yeah, I think that's okay. Yeah, because we're training models. That would be your equation. So that like you just run it through that equation.
Oh, God. Okay. And then it said results in optional homework working for features. They do that because it's really interesting, right? Yeah.
So last class we left off on finishing up linear regression and multiple linear regression. Yeah, I'm recording. Thanks for reminding me. Class looks a little smaller this week. Or is it just me? Must be the rain. Looks a lot smaller. So last week we finished off the end of linear regression, talking about applications of linear regression, and we spent most of the last lecture working through an example and sort of like doing linear regression in practice. And this lecture will be the last lecture of the course on regression, and we're going to focus on sort of two additional domains of regression, polynomial regression and logistic regression. One thing that I wanted to at least make sure I discuss, because it's very relevant to the homework, is how you do regression when there are categorical variables. Because the data set in your homework due on Thursday has a categorical variable in it. I believe it's weather. And we discussed, I mean, all the examples we've done so far have been discretely valued and continuously valued variables, but we haven't done any variables where where the variable itself is categorical. One of the problems, the short story is that you can't apply regression to categorical variables. In other words, just assign a categorical variable a value and expect to get a regression. The reason being that if I have a variable, in order for me to do any sort of regression, there's an inherent ordering to the variables that I'm doing regression over. And so let's say I have different types of weather. And this is in the bike train wheel, where I have some values where I have different types of weather, maybe say rainy, cloudy, windy, and sunny. And I create a value associated with that where I say, for whatever reason, I want to make rainy 0, cloudy 1, windy 2, and sunny 3. And maybe I did a regression, and in my regression, if I was just doing a regression on these values, maybe I was looking at the if I were to say, let's say the x-axis is weather, and I've transformed my values between 0 and 3, 0, 1, 2, and 3, and maybe I'm looking at, say, like number of rentals. And I get something that maybe looks like this, where I have a bunch of points over here at 0, and then maybe at 1 I have some sort of relationship here, and so forth. And I could theoretically plot a regression line between these points, but does it really make sense to do so? Because I sort of arbitrarily define my attributes here. So I could, these are not what you would call ordinal values. And by ordinal values, we talked about a few lectures ago, some variables have an inherent ordering to them, like days of the week, hours of day. Some variables, some categorical variables do not have an inherent ordering to them, and this is an example. There's not really any reason why rainy is 0. I could just as well say make this 3 and this 0. Right, and that would completely flip what my graph looks like. I mean, as soon as I swapped any two of these variables, then my graph would look very, very, very different, and my regression would be completely different, right? Because I'm basically interchanging values on my independent axis, which, again, it's perfectly valid because I could, just reassign values here. There's sort of an arbitrary mapping, and there's a technique, a strategy for dealing with this. It's not that you can't do regression on categorical variables. It's that you have to basically map your variables to distinct categories. There's a method in scikit-learn for doing this. The technique is called one-hot encoding. And the way it works is if I have, say, a data frame, if I have a data set where I have a set of these values, and let's say the value here is weather, the column name is weather, and I have all of these observations, and 1, 0, 3, 2, so randomly picking some. What I need to do is basically I need to transform my data frame so that these basically every value becomes a column name. So I have one column here. So I have one column with 4 factors: rainy, cloudy, windy, sunny. And I'm going to convert from one column, I'm going to go to 4 columns where I have windy as one column, I have sunny as another column, and I have rainy and cloudy as 2 additional columns. And so now, rather than having one column with 4 values, I have 4 columns. Each of these is going to have some value between 0 and 1. So in this case, where the weather was 0, I mapped 0 to sunny. So now it doesn't matter. Now I basically have a data set where the values, the ordering doesn't matter because each of them are in their own column. So sunny, this one's going to be sunny, and the rest will be 0. And here I have 1 for cloudy, and so this is going to be 1, these are all going to be 0. And same thing here, I have sunny again, this is going to be 1, these are all going to be 0. I have 3 for rainy, so rainy is going to be 1 and the rest is going to be 0. In other words, I have 1 hot, 1 hot, 1 hot, 1 hot. This is what we call one-hot encoding. And the function in the module to do this in scikit-learn is one-hot encoder. And this is what we call a pre-processing step. There's a whole module in scikit-learn called pre-processing, which is basically things that you need to do. This is what we call pre-model workflow. Stuff that you need to do to your data set, transformations that you need to apply to your data set before you can train or apply any sort of learning algorithms on them. I'll work through sort of a quick example. Create a new notebook. Import numpy as MP. Import pandas as PD. Should be pretty familiar by now. And I'm going to do matplotlib. Import matplotlib. lib.pyplot as plt. We'll inline this. And make sure, this is something that I often forget to do, is to do the matplotlib inline declaration. That's basically just what allows me to have my my plots inline, so I can say like plt dot whatever, and it will show in the same plot. I'm going to load that data set, which is 2 levels up. It's in data, and it's in bikeshare.csv. And if I load that, I can do bike share.columns. Again, this is familiar to you guys by now because it's on last homework and this homework. Some of these columns are interesting, some of them are not. But one thing we haven't covered exactly, one function we haven't covered exactly is that if I say take one column, let's look at, what is it, weather sit, I think it is in this example. Weather sit. If I do a type on this, what do I get back? If I do a type of, if I look at my data frame in terms of one of the columns, what type is it? It's actually a series object. So series is basically a data frame with one column. And if I do weather sit dot value counts, I'll call this as a function. So again, I can see that there's 4 distinct factors in my data set, where one is the most frequent, and I forget exactly which one these map to. And there's documentation. I believe this is part of the UCI data sets. Anyhow, I'm not going to dig for it right now, but we want to basically map each of these values to be their own column, and we're going to do that using sklearn one-hot encoder. And the naming conventions applied here are, so sklearn is a module. Pre-processing is a class, I believe, and one-hot coder is a class. Oh, sorry, a class within that module. So there's pre-processing is a module, and we're going to import that from sklearn.preprocessing import one-hot encoder. So now I have one-hot encoder available to me, and basically it's basically gonna do exactly what I did in that last set. It's gonna look for where there's distinct factors in my data set and convert that into something that's usable. In other words, something that fits this scheme that I have here. And again, one of the nice thing about scikit-learn versus pandas is that scikit-learn, you notice that there's certain patterns, there's certain functions that get called very often. And one of them is this .fit function. So there's .fit and there's .transform. So one-hot encoder, I build a new encoder like so. I basically just declare, I call it as a function. So I'm going to say encoder, one-hot encoder. I've just built a one-hot encoder, and then I say one-hot encoder .fit. And what this is doing is basically just transforming the input data to some alternate space. So I believe I can just pass a data frame in there. I have my data frame as bike share. And I need to say the category. So I say categorical features. I pass which one my categorical features is. I'm just going to pass this, cut and paste this for my reference. Again, we can always press Shift-Tab to see what the arguments that function calls, or what that arguments that the function expects. If I do Shift-Tab, we'll say categorical features. And the categorical features I have here, I believe, was weather sit, right? And if I do bike share weather sit, this is my categorical features. So there's 2 steps. I'm declaring the one-hot encoder here, just as I've done with other examples in scikit-learn in scikit-learn, there's a pattern where we declare the object we want to use, we build the object that we want to use. This particular type of function is called a constructor. So one hot encoder is an object. When I call this constructor, it constructs for me an object with some default values that I've passed into the constructor. And this constructor, this object, I can then call fit on, and the fit will basically it will change the state of one hot encoder, and I can get a value back. So it's going to be a value error. Only one value to unpack. I believe you need to have a bike share dot weather sit. Anyhow, I'll come back to this after break. But I just wanted to at least mention this for this class because your homework you'll need to apply the one hot encoding to the weather situation, to the weather sit variable on your assignment in order to basically do an effective regression. Also, speaking of homeworks, I want to we're missing a ton of them. Basically, I think we've only gotten 4 or 5 submissions in total. So, I mean, it's going to be an issue moving forward. If there's anything you're unclear about on the homework that was due on Thursday, it's just going to make these assignments more and more difficult moving forward. So make sure you get those in as soon as possible, preferably before Thursday, so we can grade them and provide feedback. The homework due on Thursday was particularly important because it was comprehensive of everything that we've sort of covered in the first 3 weeks. So it's concerning to me that there is such a small amount of submissions on homework 1. So make sure you have it. Make sure your name is in the pull requests, and we'll be grading the first 2 assignments this week, and so we can get those back to you. Anyhow, questions on that? How difficult? I mean, who had questions on homework number 1? I guess were there any common issues, or any common issues that people had in homework number 1? Just want to, I guess, resolve those.
Define homework number 1.
Sorry, homework that was due last Thursday. Homework number assignment 4.
This was on the bike shared data.
Yep, exactly. So the first step was going through there was an example assignment, and the second part was the bike share data. And the homework due this Thursday is doing regression on this data. So it's the same data set, but doing a regression, a multivariate regression. Okay. Anyhow, I just wanted to make that point. We left off last lecture talking about discussing caveats of linear regression, and one of the topics that we got into was sometimes you're going to be faced with data that isn't linear, that doesn't fit a very clean linear model. And I guess there were sort of 2 circumstances. We talked about regression when we want to do regression over more than one variable, and we also discussed regression when we want to do regression over a relationship between our independent variable, our x, and the target variable, which is y. And we defined our model basically as y, our target variable, is going to be some coefficient times an independent variable times beta 0, and we're trying to find really the two parameters of our model, which are beta 0 and beta 1. And this model represents a line, and this line is, the model represents our line of best fit to a series of points, which we call the model y hat. Each one of these is an observation in x and y. And we could generalize this to n dimensions by saying y is equal to some beta sub m times x sub, x beta m xm plus all the way to beta 1 x1 plus beta 0. So we can just extrapolate this linear function to really, in one dimension it's a line, in two dimensions it's a plane, and so forth. And we can basically have a data set that has if it has a high dimensionality, we can extend the concept of linear regression to fit a set of points in an n-dimensional space by applying multiple linear regression. What we didn't talk about, however, what we didn't really discuss in detail was, what if I have a nonlinear relationship between my independent variable, values in my independent variable, and values in my dependent variable? So in other words, if I have a series of points that look like this, and we sort of saw this on the TB data set, where we had a set of points that didn't necessarily fit a straight line. So you can imagine, you know, if I did a straight line across this data set, again, we'll call this y hat, it fits. Clearly there's a relationship here. But what I really want, what would ideally be even a better model is, in this case, if I had something that looked more like, say, y equals, y is some function of quadratic. And you can imagine I can sort of have something sort of like this, right, where I have my model is, rather than being just a straight line like we had in this case, my model could be a parabolic function or a quadratic function. And it could even be higher order, right? I mean, we sort of arbitrarily, we have a very complex curve or a very complex set of data points in, and we should be able to sort of extend the concept of linear regression to what we call polynomial regression. And I guess by a set of conventions, we call polynomial a type of linear regression because our coefficients, the terms that we're finding for our regression, even though in this case we have an x squared, we still call it a linear regression, a linear model. Because the coefficients of our model are linear, we still define it as a linear model. I want to work through an example of this with you guys. Let me make sure this is on the repository. One sec. Yeah, unfortunately this repository is getting a bit unmanageable, but if you pull down, if you navigate to DAT 20 NYC students now, you should be able to pull down master. And within master, under lectures, under lecture 8, you will find a notebook called Polynomial Regression. So go ahead and open up that notebook, and we'll work off of that for the first half of lecture.
Where's it located?
It's under Lecture 8, under Logistic Regression. Should look something like this.
Polynomial regression.
Yep.
Oh. Can you see the rest of your file path? Is it under exercises?
It's under Lectures. Make sure you pull down the latest and do a git stash if you have a hard time pulling it down. So if you have stuff in your working directory, just do a git stash. Otherwise, just do a git pull within the master branch. Just do git checkout master, and just do git pull. Okay, so before we talk about polynomial and regularized regression, I want to introduce you to a few functions that we'll be using that we haven't used yet in scikit-learn. I included links for these at in the notebook. One of them is called cross-validation. There's a cross-validation module in train test split. Last class we talked about the importance of splitting our data set into a training sample and between a training and a test sample. And the cross-validation train test split is very simply a function that lets you split a data set into some percentage of that data set being training and some percent of that data set being test. So if I have a data frame that looks like this, let's say this is my bike share, whatever, bike share data frame. And I have a bunch of variables, like day, weather set, rush hour, etc. And I have some target variable count, which I called CNT. This is what I call my target variable. And let's say I have 1,000 rows, 1,000 observations. It's important that I have at least that I apportion a small percentage of my data set, usually around 30%, to training and a certain amount to testing. And that depends. There's various strategies of how I validate my model. But the point is, really the most important thing is that I train my model on a different set of data than I validate my model on, right? So I have some, say, 70% of my data set which I use for training. In other words, that's what I use to build my model, that's what I'm doing to use my regression, etc. And I have, say, maybe 30%. I have 30% of the rows that I dedicate to testing. And again, sometimes one of the drawbacks of having to split my data into a training sample and a test sample is that, I mean, I'm throwing away some of the data I'm throwing away some of the data from my training set. I'm not training on my entire data set, but I need to have something to objectively, some data that's what I call my out of sample data that makes sure that my model that I've trained can generalize to samples that it has not yet seen. One thing that's important to do in the training set is to make sure that there's no inherent, before I split my data set, I want to make sure there's no inherent ordering to my data. Sometimes in a data set, if you look at, say, the first index of a data set, or the first few rows of a data set, sometimes you'll have newer rows here and older rows towards the end of the data set. It's important to shuffle before splitting your data because you want to make the least amount of assumptions on your data as possible. And if your data has any sort of ordering to it, if the data in the first half of your data frame is older than the second half, then there might be certain biases that introduces to sampling your data. You don't want there to be any biases. You want it to be as uniform as possible.
So just assume there's no correlation between any of the observations. So you're looking at a time series or something like that. This wouldn't work.
Yeah, well, I mean, it's not that it wouldn't work, but if there wasn't time ordering to your data, then it may.
Or any other correlation.
Yeah, you want. In most cases, it's going to be like a time series. Like if you're looking at a database, right? Database auto-increment. Every time it inserts a row into the database, it'll increment an ID, and it will add an additional row to that database. So, if you're pulling almost from any real data set, there's going to be some inherent time ordering based on when that observation was made.
So under that sort of assumption, would you say that if you're doing any sort of statistical or predictive modeling on perhaps like survey data, where theoretically it's kind of taking all at the same time, this sort of setting and sort of subsampling of the data is necessary to test for necessary model?
You mean the shuffling of the data isn't necessary? It's a good practice. There's no reason not to shuffle.
Okay.
You want it to be random. In other words, if I were to pick a random row from my data and say pick another row, there shouldn't be any assumptions. Like if I pick a row, if I sample a row here, and I sample a row at the end of my data set, there shouldn't be any meaningful difference in the values of the variables I might expect. So if there was like a date column in here, right? And this is actually the case in the bike share data set, where there is a degree of the rows at the beginning are older than the rows at the end. And so if I sampled something from the beginning of the data set, I would know. I wouldn't be getting a random sample from the data set. And there's basically the pre-processing module in scikit-learn does this. There's a random state which it uses to shuffle. So it inherently shuffles it by default. But I just want to sort of show you how this works. It's in this sklearn.crossvalidation.trainTestSplit. So within this, I'm going to say train test split. If I declared, say, like an x, say my x variable, and I had this as import pandas as well, and I say pd.series, just creating a series object. If I evaluate that, and then I say train test split, well, I guess I'll need two. I'll need one for my x and one for my y. So let's declare a dictionary. And I'll take this and I'll say, again, I can construct a data frame. A data frame is very much like a dictionary. And so if I say, this is my x variable, and say I have some y variable, and I'll sort of add one just so that these are distinct. say bd.dataframe. Let's call this df. Comma. And then if I call train test split, I'm going to basically say, I'm going to separate, in this data frame, I'm going to separate the variables, my target variables, which is my y, and my input feature variables. So I'll call this x1 and x2. And just to make them visually distinct, I'll make these negatives. And again, this is just an example. I'm just artificially creating a very small data set. And I want to split this data set.
You did x1 twice.
Oh, I did x1 twice, yeah. This one array argument. Oh, yeah, to change a split, I'll say x. Oftentimes, just mathematically, we denote x or input variable because it's a matrix. In other words, if I were to represent this as a matrix, I'll show you guys in a second, but I can just select x1 and x2, those two columns for being x. And for y, I can just say df.drop, drop y. Or better yet, I can just select that value independently. So now I have item, oops. So now I have, I'm missing df.loc. So y, what am I missing here? Is it spelled wrong? No. Sorry guys, I'm having a total brain fart here. I'll just do this. Do df.drop x1, x2, and say axis equals 0. Anyone have any ideas? Because I'm all out. x1, x2.
You're trying to drop features.
And I'm just trying to select the x1 and the x2. This is what happens when you code in Ruby all day and then you come and teach a class on pandas. So I'm going to say ix, and I should be able to index these using ix. So x2, key error x1. x2. No idea. Anyhow, I selected, we'll just do 1. So we'll do x and y. We'll look at x1. And we'll do train test split on x and y. And train test split returns 4 different values. So basically, it'll split my data. So if I have a data frame, it will split it basically based on some percentage, right? So if I say this is 70% of my data, and this is 30% of my data, it will split this into basically two data sets. So I have, this is say my y, and this is my x. It'll return two values. This would be x train. This would be y train. This would be x test. And this would be y test. And so what I get when I get back, you can see each one of these has 10 values, and so it's basically splitting the data here. So if I can assign this as being x train, y train, it returns basically an array, and I say x test, y test equals train test split. And so now when I print each of those, maybe make it a little clearer. Y train, x test. So again, let's break this down, get rid of the x2. I have my x and my y, and just make this further clear. I've basically just split my data frame into different pieces. So x train and y train are going to be what I'm going to be using when training my model. And the testing portion is what I'm going to be using when I test my model. And just so I make it clear, there's also a percentage that I pass in cross-validation. There's the train size, and I can basically just say, I'll say test size equals 30%. So 0.3, and I'll get 30% of the training and test set. Makes sense. So in other words, when I train my model, I'm going to be using the training set, and when I test it, I'm going to be using the test set. Also, another important tool, another important module is the make pipeline. And oftentimes you'll find that you're doing multiple steps in a row. What pipeline does is it basically allows us to specify a series of transformations to our data all at once, rather than doing it one after another. So, for instance, if I'm given some data set. A pipeline is basically a series of steps that I apply to my data. So sometimes, for instance, I have, so X is say my data set, and I have some step like, say, maybe one-hot encoding could be an example. And then the next step, I basically scale my points. And then in the next step, I basically build the train/test split. And what I get back is some transformed value of what I put in. And so oftentimes you see pipeline being used. It allows me it gives me a reusable, consistent way of applying a series of steps to my input. That's more succinct than having to. Pass. Basically have like large functions and pass this stuff around in independent steps. Oftentimes maybe you have something like where you're applying a series of steps, like you have some data frame, and then maybe you say you truncate that to the first 1,000 rows, and then you do something like, like you filter, you only select part of the data frame, just do data frame.drop, etc. Pipeline just allows you to sort of, in a single statement, apply a series of steps and their parameters to do a series of tasks. And if it's not clear, I think we'll cover this also later in this, directly in this exercise. So basically I have here an example. I'm not going to declare all of these or go through this line by line. Most of the stuff here, again, is familiar stuff that we've done. There's a few new things that are being applied here, a few new modules that we haven't used, some of which we just talked about, like the train test split, polynomial features, and make pipeline. And so these 4 are topics we'll be discussing that are new to this class. The first thing I'm going to do is I'm basically going to declare my figure, and I'm going to declare a sine function. So obviously, a sinusoidal function is not a linear function. And so we're going to be trying to, we have a function that looks like a sinusoid, and we're going to be trying to we have a series of data points, that fit some sinusoidal function. And we're going to basically attempt to define some function that can most closely fit those sets of points. I start by declaring a simple function, which is just really wrapping the np.sine function. The np.sine just takes some input and just applies a sine, just like a sine on your TI-86 calculator or whatever. And then I'm applying this np.random.uniform. I'm applying some randomness to every value in my sample. So if I looked at x initially, by the way, np.linspace, what linspace does is I'm declaring a range of values in the first 2 arguments, and I define the number of splits between those 2 values. So if I did np.linspace and between 0 and 1 and gave 10, this would give me 0.1, 0.2, 0.3, etc. If I did linspace between 0 and 100, it would just sort of divide each of these by 10. So it's giving me 10 values evenly distributed between the min and the max. And it's just a quick way of defining, if you want to define a function and define each of the samples along x for your function, you could call np.linspace. And so I've declared the number of samples, and I'm applying a certain degree of randomness to each of my samples. So if I say took out this random.uniform, they would all lie directly on top of this sinusoidal function. I just apply a certain amount of randomness because, obviously we're trying to plot regression, and we want this degree of randomness represents the error that we have from our input value. And so then I define my splits, my x train, my x test, and my y splits. And I'm taking my test size here. In other words, I'm just sampling 20%. So my test size represents 80% of my data in this case. And so 20% of my data is left for sampling. And then I just simply plot it. I'll bring this down a bit. I'll give you guys a few minutes just to catch up. But any questions so far? So I plotted an approximate, yeah.
So I think you used this last class as well. It's between 2 brackets. It's like colon, comma, np.new axis. Like, what is that?
Yeah, so what np.new axis does is it's basically turning a one-dimensional array into a matrix. So scikit-learn doesn't actually natively support everything that pandas offers. And so when I say, if I run this and if I do xplot, right? Xplot is basically just a range of my values. It's 100 values ranging between my 0 and my 1. If I do x.plot and I do this, I get the same thing. But what np.newAxis does, and if I look at the shape, you can call shape on a data frame, and I get 100 rows and undefined columns, right? But if I do, and this is the distinction, if I do plot np.newAxis, I get 100 rows with 1 column. So it's basically giving it a degree of dimensionality. And it's I guess a little confusing because if I don't do that, pandas will complain, and it expects to see, basically a matrix, and I'm passing it a pandas vector. And it's just sort of a quick of pandas. But when I plot these, they look effectively the same, and they behave effectively the same if I'm just looking within PyPlot. But that's the distinction. The np.newAxis forces it to be evaluated as though it were a matrix. So you can see now it basically gives me, it formats a little bit differently, and it wraps it as basically a bunch of these arrays within a larger array. Whereas this is just one big array. np.newAxis, again, just gives me, it just forces it to be, forces it to be matrix. Any other questions? Okay. Okay, so I've plotted this. I've plotted this basic sinusoidal function, and well, what will we get if I do a linear regression on these set of points? I mean, obviously, I'll get something that sort of a line that vaguely fits along these points. So just sort of recap last class. I declare basically just a simple subplot here, and declare the degree 1. And another topic or another function of scikit-learn that I want to introduce you is to this preprocessing.polynomial features. When I look at a, I'll sort of plot the first few values of my X train. Come back to this in a second. Yeah. Better? All right. So I have my training set. And again, this is just a one-dimensional training set. Same thing, same goes for Y-train. It's just a one-dimensional training set. I'm going to just basically select the first, say, 4 values. Actually, make it 10. Make it 5. Also, I mentioned this class before, but just want to reiterate. When I do basically this colon here, I'm basically just selecting a subset. It's the same as going from 0 to 5. So basically selecting row. This is row 0. This is row 1, 2, 3, and 4. I can omit the 0, and Python is happy to basically, this is called slicing the first 5 rows of this matrix. When I'm transforming this to what I'm doing really is I have a set of variables along x, and so when I'm fitting a polynomial, when I'm fitting based on 2 terms, let's say I have a data frame that looks something like this, where this is my x. So 1, 2, 3, 2, whatever. And I can have many rows here, but I have one string here for x, and I now need to create another row here for x squared, don't I? I have this x squared here. Previously in linear regression, we weren't concerned with x squared. So I'll have basically, if this series is just x, then I need to calculate x squared, which is just going to be 1, 9, 16, 4, 9, and so forth. And this polynomial features in scikit-learn is just a way of doing that. Sort of cut and paste this into my workbook so we can sort of cross-reference that. When I generate, if I do polynomial features, and again, just sort of using give you a concrete example of what I drew up there. So let's say I have 1, 2, 1, 3, 4, 2, 3. If I call polynomial features on x, and I'll declare this as an numpy.array, this in this x variable, if I just have a bare x variable, this is going to be, again, just a vanilla, x is just a vanilla Python array. If I say type panda.series, or sorry, np.array, that's how I convert a array in Python to an array in NumPy, and it just considers it to be an ND array. So I'll say polynomial features x degree equals 2, and I'll call this x poly, and I'll call it x poly features. And what I've done is I've constructed a polynomial features object, declaring it with degree equals 2. And so when I say x poly features, I believe it's transform. There's a transform function, so I declare it and then I do a fit transform on that, on my array. And I'll reassign x here using np.array x. In other words, I'm converting it just from a simple list to a NumPy array. And what I get back is basically, make this a little short. It's a little hard to see, but let's do degree 1, and you can see basically what I get is we're trying to fit, when we called, this term here is basically our beta 0, right? If we're looking at the coefficient of x for beta 0, this is always going to be 1. And so when you do the fit transform, I see basically I need to transpose this to get the right value, but you'll always see that it gives an extra row vector for the 1. I need to, again, do x. I need to do the new axis. Equals and yeah, so you can see I have here these sets of 1. So this is what I have here is this first column this first column of values is my beta sub 0. And the coefficient for, sorry, it's 1 basically for my beta sub 0. This is the set of values that are for my x, and this is my x squared value, right? And so what I really have, if I sort of map out these values, I'll put it over here so I have room. What I'm really trying to find is my model y equals, in this case I've declared I have a second degree polynomial, so I'm trying to find some beta 2 x squared plus beta 1 times x plus beta sub 0. And really beta sub 0 is the same thing as beta sub 0 times 1. And that's why, really, this is my beta sub 0. I have one, that's my one multiplier. My x multiplier for beta 1 is this list of vectors. Again, that's just the x's that I applied up here. Notice the consistency between my x vector and my first set, my beta sub 1. And it also maps x squared. This is just x squared, isn't it? And, you know, again, when I was doing simple linear regression, I was just looking at this. And if we were to sort of look at it from the perspective of, oftentimes when we're dealing with these sort of equations with many terms, we write a shorthand. We use notation called vector notation, or matrix notation. And I can say basically, this is for 2, this is for a polynomial of n equals 2, this is a polynomial for n equals 1. And so for n equals 1, I can basically say x1 times 1. If x is a matrix and b is a matrix, then I'm really just multiplying. I call this my matrix x, and I call this my matrix beta. And I can say y hat. I can basically apply 1 by 1 to get y hat is my x vector times beta. By the way, actually, I should just sort of make one thing clear. If I have, say, a vector beta, and vector beta is a row vector. We call this a row vector, and we call a vector. In other words, there's one row, and there's 2 columns. So we say beta, the matrix beta is in the element of 1 by 2. And so in order to multiply, basically when I'm multiplying two matrices, I'm multiplying each row by each column. So I would basically, if I would need to transpose beta. And if I do x times beta here, this is the same thing. This is mathematically equivalent as saying x1 times beta 1 plus 1 times beta 0. And if I did this again in the polynomial case, I would have a vector that looks like, my x vector looks like what? It looks like x squared, and I have x, and then I have 1. And then for beta, my beta vector looks like beta 2, beta 1, and beta sub 0. And so if I define y hat in the second case, in this case, then I'm going to be saying beta 2 times x squared plus beta 1 times x plus beta sub 0. And again, this 1 here is this set of 1s here. This is my x, and this is my x squared. So again, this is just when I'm applying these this polynomial features, this transform. It's just transforming this x vector, and it's adding the x squared values and the x to the 0 values, right? So x to the 0, x any number to the raised to the 0 power is 1, and so we're actually just seeing the sort of the 0 with order term. Okay. So sort of moving on to like a concrete example, right? I can I can basically go back and, if it's on this, I can make my pipeline. So the first thing I'm doing, again, I'm applying a series of discrete steps in sequence. The first thing I'm doing is I'm declaring I'm transforming my input vector, my x I'm transforming my vector into something that fits fits the format that I'm looking for. So I've just taken x and I've turned it into a set of polynomial features, which I'm going to do my regression now. So now instead of regressing on the features that make up a line, I'm going to be regressing on the features that make up a polynomial. So this is the step one, and I'll sort of put this in line with the rest of my example. So step one, transform my input into a polynomial feature space. And I'll paste this sort of as example output. And again, my example input was x equals some 1, 3, 4, 2, 3. And my example output fits my higher order array. This is step one. And then step two, again, we did this just the same as we did last class. Step two is apply linear regression. So we're actually applying the same form of regression, and this is why I made the point earlier that when we do polynomial regression, it's just a general case of linear regression. We're just transforming our input data into a form that takes into account the nonlinear interactions between terms, but we're still applying the exact same transform, the linear regression. So when I call make pipeline, all I'm doing is just chaining those two steps into a single step. So I'll put these up here, sort of being part of my example. Okay, so applying linear regression is just the second step of my pipeline, and the pipeline basically acts, again, you're seeing this fit function being called again, and you'll see this fit function in scikit-learn time and time again. We saw it last class, we're seeing it this class, we'll probably be seeing it in many classes to come. But really, what the fit does is that's just building my model. What fit is doing is it's determining the coefficients that fit the model. This is what we call fitting y hat. And this is basically the .fit function. Take out all the stuff I did earlier. It's just noise at this point. And so running this, I get a new plot. And all we're doing, again, the only thing that's plotting new is this red line, right? There's a plot approximation function, which I declared here earlier, which is just taking the same stuff that we did last class and the class before it, applying the same plotting principles. The only thing that's really new here is the make pipeline and the polynomial features. But we're not actually using any new modeling techniques. All that we're changing is how we pre-process our data before we we fit the regression. And so again, this was done with a first degree. This is just basic linear regression. I'm calling polynomial features with degree of 1, and this is really the same thing as doing. It's not applying a transform in the data yet. But if you can imagine, if I increase the degree, I'm going to start getting a fit that's quadratic, and then a cubic, and so forth. And so just sort of give you guys something to do, sort of allow you guys to sort of extend this concept. In the workbook, you have three sort of options: fit a polynomial of degree 2, fit a polynomial of degree 3, and then fit a polynomial of degree 9. And plot each of those in sequence, and let me see what you get. And we'll give this 10 minutes.
Can I see your code from section?
Yeah, do you want me to scroll up here?
Yeah.
You should have this in your workbook. So the only thing I added to the workbook was the comments that are in line here. But that's just a demonstration.
Yeah, I just getting here.
That might be the API access thing. This actually, in your case, section 3 is, I think you have two variables, so that's why I say by convention, I always put a capital X for train because mathematically, X is usually a matrix, and so we would express the capital.
Alright. Thanks. Oh yeah, I see this here. It's in the tuple.
Yeah. The X train is defined somewhere in the other place, so it's thinking, I don't know where it's defined. Maybe an example of that.
Yeah, clear the kernel.
You can do that, you can use that. Of course. Cool. Is everyone able to run the book again? So make sure that everyone's able to follow along. Are you able to run this one? It might be the case that maybe the notebook server was running the wrong folder. So make sure it's always pay attention to which folder you're running the Python. It might be that. That's a concept. Got it? You want to run anything okay?
Yeah.
We'll get to that later.
Yeah, okay, so otherwise, yeah.
Anthony, you get the base coefficients, you just have to run the transform.
Yep.
Oh, that's it.
Take the
Is that everything? Let's go ahead. Okay, so I think this is pretty straightforward. So let's sort of go through it and then understand really what's going on. So we're going to copy and paste this into the next cell. And if I turn the degree up to 2, if I turn the degree up to 2, is that every time I increase the degree of my polynomial, so what am I getting here? So I increase the degree of my polynomial, and I get something that's kind of like a line, but not quite. You can see that increasing the degree, what I have here is a polynomial. I have basically a parabola, a quadratic function that's sort of approximating a line. As I increase, if I do a degree of 3, so the degree of 3 is actually a pretty good fit, right? I mean, that sort of makes sense, because a sinusoid in the domain of 0 to 1 kind of looks like a third-order polynomial. Every time I turn that up, though, if I go all the way up to 9, now I get something that starts to look kind of weird. I can turn this way up, by the way. I mean, there's really like no limit, right? So what I have here is I have a function. It's kind of crazy. I'll turn it back down to, say, 9. What has, I mean, going back to our discussions earlier, talking about residual and r squared, what's the r squared here? I mean, just an estimate. Well, I guess a better question is, what has a better r squared? This red line here, or this one here? So I make it. Yeah, if the second one has a better r squared. In other words, mathematically speaking, quantitatively speaking, in the context of this example, in the context of my training set, this red line fits the data well. But is it a good model? Well, probably not. Why not?
Overfitting.
It's overfitting, but what does that mean?
Conform to just the training data set. It fits that one very well.
Yeah, so it fits this, it fits this data very, very well. But you can imagine that, I mean, this has these crazy values at the extrema, right? Because it's a high order polynomial, it's basically shooting up towards infinity, and shooting down towards infinity. So every time I add a term, it's adding really like another one of these humps. And so if I start making observations over here or anywhere, it's making observations that fit the data very well. But these observations do not generalize to out-of-sample observations. This is what we call generalization error. The in-sample error is low, the out-of-sample error is high. And we call this overfitting. And it can happen with linear functions, but it is more of an issue. It is more of a problem with polynomial regressions. And really, the point of this is to see the difference between, or really the cost of going to high degree polynomial terms. So what I've done is basically increase the complexity of my model. And because it's a more complex function, every time I add a degree to my model, this plot here, I'll blow this up a little bit. So what I've done is I've every time, let's look at the, let's say I have a set of data points. And in my case, it looks something like this. Sort of fits a sinusoid, right? And again, each of these points is a value of x. And so when I fit a line, the line has This is degree equals 1. Degree equals 1. And when I fit a polynomial, what I get, when I fit a quadratic, I get something like this, and the degree equals 2. And then I plot another function, and this is degree equals 3. I won't plot every single point, but eventually I go up to degree equals 9. And what happens when I go to degree equals 9 is I'm getting something that looks kind of like and this very, very complex function is degree equals 9. So if we plot a graph, let's sort of see what our function looks like. So this is, each one of these blue data points is, this is in our training set, right? This is within X train. And eventually, so this is, let me say, maybe 80% of my data set. And so when I look at samples that are not within my data set, they don't necessarily fit along these lines, right? In the interest of keeping this less cluttered, I can really have a cost function, or I could sort of evaluate my model on both in sample and out of sample. So let's say along here, I have this function, along here I have the degree of my model. And what I have here is I started at degree 1, I plotted that, and then you guys plotted degree 2, 3, and eventually we did all the way up to degree 9. And let's look at both the R squared, or really the error of our model. And for degree 1, when I did degree 1, I had a reasonably high degree of error, right? So the error so this is the error of my training data set, and the degree of error on my test data set is probably a little bit higher. So my error of the test data set, my green data points. And what happened is every time I add a term, my test training error goes down. So this is at degree 2, this is degree 3, 4, 5, 6, 7, 8, 9. So increasing the complexity of my model, because what my regression algorithm is doing is finding the best fit, it's going to always decrease. And so it gets lower and lower and lower. In other words, if I were just going by my training data set, if all I cared about was optimizing my training data set, every time I add a degree, it goes down in error. That's what's happening here, right? So I add a degree, and then all of a sudden I get to these higher and higher order data points, and it doesn't change much. But my test data set, I see a different story. So my test data set, what happens is, it decreases at first. In other words, yeah, this function that I plotted here clearly isn't a linear function. So it makes sense that for a degree of 1, I'd have a reasonably high degree of error. And as I increase the order, it still decreases a little bit. But then eventually, as the degree of my model increases, my test error increases. My test error increases. And so, really, I want to, the optimal degree of my model is somewhere probably along where I'm minimizing my test error. This is sort of like maybe the optimal degree of my function. And we talked a lot last couple of classes about R squared. We want to minimize this cost function, right? And to a degree, that's true. We want to minimize the cost of our model. We want to maximize the fit of our polynomial model on the training set. But really, what matters, my ground truth, the one ground truth that I have is how well my model generalizes to observations that I have not yet seen. And so it's a requirement that I have R squared, not only, a low R squared, not only on my test data set, but on my training data set as well. And so this is really why it's important to split between, or have a reasonable split between my testing data and my training data. And this method of evaluating my training data and my test data separately is what I call cross-validation.
What was the ground truth again?
The ground truth is how well, minimizing the out-of-sample error. In other words, my model should be able to make predictions with as little error possible on observations that it has not yet seen. This is my out-of-sample error. This is my in-sample error. So this is what I call out-of-sample error. The blue line is my in-sample error.
Let's say like relative, like this graph we're seeing right here. The red line is your linear regression, right?
It's the regression that was built on the training data only.
And the green line?
The green line is just sort of like the original function. So it's the true function. In other words, what I did was I defined a sinusoidal function. And I defined 100 points between, I just subsampled the first 20, and I added a degree of noise to each one of those points. So it's saying, evaluate whatever this green line is, and then add some error. And so the green line is the true function that my data was trained on. The red line is what I get when I fit a high degree model. When I fit a linear model, when I fit basically a first order model, we'll say, I got this straight line. And it wasn't a great fit. It told some relationship within the data, but didn't capture the true relationship. And so really, as I increased the degree, you can see that with second order, it does a little bit of a better job. In other words, as I increase the order of my function, degree 3 seems to be about the sweet spot. Because as soon as I start, it approaches, the ground truth is the true model that the data was generated from, and the red line should be as close to that green line as possible.
The green is on the entire data set, trained plus test.
Yeah, right. So, but when I increase my degree very, very high, again, it's just fitting these individual points. So a single outlier in each one of these points is going to shift my model considerably. And so I want to basically be able to plot additional points on this graph and have less error on observations that are not within these blue points. Yeah.
So as the percentage of, like, the proportion of in-sample to out-of-sample changes, like, doesn't that graph, the illustration, shift a little bit? So, like, is there, like, an optimal percentage that you should use as in-sample versus when you're doing these types of sort of iterative tests? Or, like, when you're just playing around?
That's a really good question, and the answer is there isn't an exact percentage. So there's actually a variety of techniques that we'll talk about in the future when we talk about how we can. The problem is that we're splitting our data, and so we're sort of throwing away some of our data so that we can train it. And there isn't, traditionally, when you're doing a simple split, it's about 30%, 70% train. So 30% test, 70% train. But you can imagine that I can run a model, I can evaluate a model multiple times on different data sets. So I could say, split my data set into 10 different sections, right? So if this is my data set, this is what we call k-fold validation, where I split it into multiple points. And I say, okay, I'm just going to look at, maybe 10%. This is going to be my training data set. my testing data set, and I'm going to train on 90%, I'm going to test on 10%. And then the next time around, I'm going to go one over and say, I'm going to do 10%, 90%, but I'm going to do a 10% split on a different section of data. And this is what we call sort of like this rolling analysis is what we call k-fold validation. And the benefit is that I can throw away smaller amounts of data to my test data set. But more importantly, I can do it multiple times on different sections of the data. And the drawback is that it's computationally more. I have to do my regression. I have to build my model 10 times and evaluate it 10 times. But I'm more certain on my overall evaluation of my model because I've run 10 independent analyses on a larger training set. I'm more confident on the result that I get. And there's a variety of what's called cross-validation techniques that we'll use. You can imagine if I can even go to the extreme and I can say this is what we call a leave one out validation, where I remove one sample into my test dating set. So I do like 99.9% of my data set is the training data set, and that 0.01% is my test data set. So I can get very, very granular on how I get my data set, but run many evaluations of the model. And that's generally the trend that you see, because it can be very, very computationally cumbersome to do. But when you use that approach, you have a more confident model.
Isn't it also a function of how confident you are that your sample size actually approaches the real function?
That's actually a really good point, and yes, to a degree. This is also another thing that we'll talk about on how large a sample size needs to be in order to have confidence. But you very quickly reach diminishing returns. So if you have 10 samples, if your entire data set is 10 samples, 20 samples, 50 samples, you're not going to get a very reliable regression unless there's a very, very, very strong relationship between two variables. But in general, you need typically thousands, at least hundreds of data points before you can start being confident. And there isn't really a hard and fast rule, but you get past a point where having more data doesn't necessarily improve your evaluation. You can sort of think of the central limit theorem. If you're familiar with statistics, eventually the standard deviation of a sample decreases with about 1 over the square root of n. And so it's sort of like a square root, you sort of like reach a sort of square root approximation where the size of your sample set increases, but you don't really improve your...
Two lessons ago, and I think it's in the next notebook as well, if you're doing something which has a logistic regression, trying to predict a sort of failure or a default or something like that, and the probability that default is low, then your sample size has to be we're predicting failure out of a large sample.
That is where if you have unbiased classes, and we'll talk about this actually very, very soon, but we're doing a classification problem.
Yes.
And you have a set of classes that are disproportionately represented. In other words, if you're doing like cancer, right? And so like 99% of the time you don't have cancer, but 0.1% of the time you do. You have to factor in weighting in order to have an effective result. Because you could imagine, I could have a diagnostic test that just predicts false 100% of the time, and it's going to be 99.9% accurate. Which is why it's easy to sort of like lie with statistics. Like sometimes you see these things on TV where it's like 99.9% accurate. But what does that mean? It means to be just predicting false all the time. And so we'll talk about this in a little bit, evaluating F1 scores and precision and recall. But that's a classification problem. This is sort of regression. Yeah, and there are some differences between the two. Yeah, so I guess really when you're training a model, the model should be as simple as possible that fits the data. So in this case, we see that increasing the model past degree 3 does not dramatically increase either, or really it doesn't minimize either the training or the testing error. And this is a principle you see a lot in math and statistics. It's called Occam's razor. Is that the simplest model that explains the data is the best model. In this case, degree 3. Looking at this cross-validation curve, we can assert with reasonable degree of confidence that degree 3 is our best bet. I also just sort of like want to summarize what that looks like. Sort of the concept of regularization and you can imagine that in this example, right, both of these models, the green and the blue model, fit the data exactly the same. And they fit it with really minimal error. But green is obviously the better choice. Green doesn't make as many assumptions. When we have a higher order model, the higher order model adds unnecessary information. It makes certain assumptions that we don't want to make if we don't have to. And so we want to really minimize the complexity. Unfortunately, I don't know why this is rendering improperly, but we want to penalize a model that has a high order. And the process of penalizing a highly complex model is what we call regularization. And so when we look at, we talked about finding or applying a cost function of a model. And we defined our cost function of a model if we're using sort of this formula here. We have the cost of a model is the sum squared difference between each one of these observations and the regression line. So we're basically summing up each of these residuals. We call each one of these observations yi. This is yi. And this line is y hat. So we're summing up the differences between yi and y hat, and we're squaring the difference. And we want to minimize basically the cost of y. But every time we add one of these beta terms, again, you can imagine that I can generalize this. I can generalize this like so. If I have in the case of polynomial regression, I'm adding these beta terms, and I don't want to add beta terms, so I'm going to apply an additional cost here that applies the cost of the beta I term associated with that point. So this would be beta j, and then this would be squared. So you'll see this. I can basically add a term. In other words, the more terms of beta I apply, the higher my cost function, right? And so it will bias towards, if I have a regression model if I have a cost function that takes into account summing up each of these beta terms, then it will bias towards the lower order of the model. By the way, so j is in the element from j to m. So if I have m features in my model, that's the number of beta terms that I have, then this is going to be the sum of each of those beta terms. And I call this basically regularization. Regularization. And it seeks to sort of smooth out that curve and keep my model as simple as possible. And there's two sort of strategies. There's the L1 norm, so I can either apply beta sub j or beta sub j squared. Typically, you see the L2 norm more commonly. But yeah, I mean, when we evaluate models, we have to take into account the complexity of the model, because if we don't, then our regression is going to basically build the most complex model possible. I mean, you can just think about it. If I'm looking at training data, then it's going to bias towards generating a complex model. And so the regularization is a way of fighting that, of minimizing that cost.
What is the S?
Is the S?
Yeah, so sum of beta squared is less than S.
So S is basically the total amount of cost. Basically, it's the upper bound. It's the upper bound on my error. So in this case, it's just a constant. I want it less than some value. So in other words, my error due to having a complex model should be less than the error of my samples. In other words, it's where this sort of sweet spot is. So we'll call this basically our sweet spot. Does that make sense? We don't. It's not necessarily. It's not something that we calculate that there's like a fixed value for. But You can imagine that if I have too simple of a model, it doesn't properly model the data. So if I'm here, this is too simple. And if I'm here, this means it's too complex. Questions? You look like you're very confused.
No, I'm not confused. I'm just thinking, if you assume that there's an error term which is normally distributed for each fit, can't you somehow arrive at a best fit?
Well, not for each fit, for each data point.
Right.
And yes, you're right. You can, and that's
To the actual, right.
there are other methods, but
Is this a priori, like defining the cost of each error, of each degree of complexity?
is it a priori? I mean, what do you mean by a priori?
Well, it seems like you've got, I'm not sure how you determine the cost, the regularization, the cost function for the degree of complexity. Is there a specific calculation?
That's why I mentioned that the ground truth is the difference between your test and the difference between the test and the training model. But the answer is that there isn't a closed form solution for it. So no, there is not an a priori. We need to basically plot each of these degrees and sort of find where the sweet spot is manually. And typically we do this, we control the amount of overfitting. You can imagine we can have basically a multiplier. We can apply some constant here, call this constant k, sometimes it's called lambda. We can apply this constant here to basically scale how much I want this regularization, how much I want to penalize my highly complex models. But I don't know k until I have basically exhaustively tried. There isn't a short and simple way to find what the regularization parameter should be.
So the outer sample error is not monotonic in regard to this.
The in-sample error is monotonically decreasing, but the out-sample error is not. Like this isn't like a parabola. It's not as simple. Like you can't like apply a derivative and find it empirically, right? Because it does depend on my data set, and it depends also. I mean, whether or not my data it's not always going to be normally distributed. It's not always going to have certain underlying assumptions, and so this is not going to fit some well-defined mathematical function.
So practically, do you penalize it more if you feel like your underlying data set is lower quality?
Well, if my data set were lower quality, if I had a higher degree of variance, then there would be a larger spread between my in-sample, my out-of-sample error. In other words, I would have more of a separation here. But I would still see this sort of convex function in my out-of-sample error, most likely, as long as my data set were large enough. And so, really, I can plot each degree of the model, even if it's a high degree of error. But really, when the data is noisier, both of these are just going to move up, and they're going to sort of move apart from each other. So to answer your question is that it depends less on the data and depends more on the technique for solving it is the same regardless of how noisy or dirty the data is. But if the data is noisy or dirty, then you might if you're getting an error that's consistently high, then that's a signal that your model is not, or that your data is maybe too dirty to effectively have any confidence. Okay, so it's 8:15 right now. Let's give a 10-minute break, and then we're going to talk about sort of like the next type of regression, which is logistic regression. So right now, so far, we've talked about regression in the context of continuous variables, both in X and in Y, and now we're going to discuss what if we want to use classification? What if we want to use regression as a means to classify an outcome, which you saw in the pre-class example? But there's also cases where if we want to use regression to detect a set of discrete outcomes of an event. And so we'll discuss that after the break, and we'll come back. We'll reconvene at, let's say, 8:25.
Oh, oh, yeah.
It's gonna be as well as happy to move forward. Right. No. See what the answers are.
So when you did dot fit transform,
Mhm.
what does that do again?
So the first one, so dot fit fits the model. So the way it works is dot fit trains the model. Transform fits observations that you haven't yet seen. So if I give you some data points, so let's say I have in SPLearn, I have a linear model. Right, so if I say LM equals linear model, I say LM dot fit, and let's say I have, by the way, if I have some X and Y, and I say that fit X, now what fit X is basically defines this this Y hat, right? And so if I call that fit, I call LM dot based on COEF underscore, this will give me my coefficients.
So this is degree equals 1, so you'll get like 1 coefficient.
You'll get one coefficient and one y-intercept, yeah. And then if I do lm.transform, so now, I mean, the whole point of fitting this model is so I can make predictions. So if I say, let's say I have to make some new observation, say xk, then lm.fit will give me what the yk is that fits to that xk. So if I say lm.fit, and sorry, transform, if I say lm.transform, and I say it would have to be wrapped in basically an array, because it expects an array. But it will basically return, I guess you could do print, right? And it will basically print what yk is. Does that make sense?
So just return 1 value.
Yeah, but I can basically have a bunch of values, right? So I can imagine I have like xk plus 1, etc. And so when I do transform, it's going to give me all of these values that I pass in. How they fit to the accorded model, how they fit to the fit model. So I guess there's always 2 phases. One is fit, and 2 is transform. And sometimes you will sort of see like a complement function which is called fit transform.
It just does both.
Yeah, because both one after the other. It chains them.
Okay.
Sorry, can you just reiterate? I know you just said this, but can you reiterate what the transform is?
Yeah, so transform accepts new data and it fits them to the model. So fit defines the model. This is fit's model. Fit transform gives predicted value from new observations. So if these are new observations, so fit generates my line, in other words, generates a coefficient, and transform maps some new variables to some output variables, which coincide with this line. Does that make sense? Okay. Before we move on, I want to solidify the concept of the bias variance trade-off. We talked about sort of these 2 extremes in that example, where we have some function that has maybe some complex relationship between the independent variable and the dependent variable. In other words, a nonlinear relationship. So we have something that looks something like this, and we're given the option, we can sort of have 3 different extremes. We have one model, we'll call this y hat sub 1, that is linear. And then we have another function that fits, say, like this. And this is y hat sub 2, and this is cubic. And then we have some crazy nth order polynomial that looks something like this. And we have, say, y hat sub 3. And this is, say, higher order polynomial, maybe n equals 7. And we just find a relationship. So we actually looked at what the error was as a function of the order of the polynomial. And this is basically the error. And so when we had the first degree polynomial, we had a reasonable degree of error. Right, so if I look at, so this is my training data. And I fit two sets of models, one on my training data, one on my test. And my training data monotonically decreases over time. Or sorry, not over time, over complexity. So this is the training data. And this is, as I go from left to right, I have an increasing complexity. In other words, a more complex polynomial. And when I look at my training data, I get something that also decreases, at least initially, but then the error increases. And I called this my out-of-sample error. And I called this my in-sample error. And again, why does my in-sample error always decrease, monotonically decrease as I increase the complexity of my, why doesn't it ever increase?
Reducing degrees of freedom. Reducing degrees of freedom.
No. No, it doesn't have anything to do with degrees of freedom. What would it mean? What would it mean if my training error increased?
Well, if your training error increases, can you just, your sort of high degree level, can you just put a 0 as that coefficient? Like at the minimum, it would have to stay the same.
Right, at a minimum it would have to stay the same. I mean, the whole point, my regression algorithm is minimizing, it's finding the curve of best fit. And so every time I increase the order of my polynomial, I'm increasing really the amount of the complexity of my model it has to fit the training data. And so it fits the training data very well. And so every time I increase my, imagine if I had like a 20th order polynomial, it could basically connect the dots, and it could, because it's a very complex function, it could just go and do this, right? And I would get a model that's sort of this beast of a model, this 20th order model, and it has basically 0 error. It's way out over here, but the out of sample error is really huge because it's over. This is what we call overfitting. And this is sort of where our out of sample error reaches a minimum. This is really what I call our sweet spot. This is, call this the sweet spot. This is where we want to be. In other words, it's not too complex, it's not too simple. It's sort of our Goldilocks zone of complexity. And points to the left of this are what we call high bias regions. So if I sort of like divide this line straight down the middle, this is high bias. We call this high bias, and we call this regime high variance. The reason we call it high variance is because you can imagine if I have a higher order model, every time I see a new sample of data. So let's say I train a model in some corpus, some training set of data, and all of a sudden I get a new batch of data. my out of sample error, the amount of difference that I see, the difference in error that I'm going to see in new observations in my high variance model is going to be high. It's going to vary a lot. So on the training data, it was spot on because it was training on that data. But anything outside of that training data, it's either going to have high error, low error. I mean, it's going to be all over the board. The high bias, on the other hand, is going to be generally inaccurate. But it has less inaccuracy on average. It's less accurate on my training data, but it's also going to be less lower error. And so you can sort of imagine if I was sort of like plotting these like a target. The high variance is going to, it's always going to be off. High variance is always going to be sort of like all over the map. If it's high bias, low variance, it's always going to be inaccurate, but it's sort of inaccurate in the same way. If I have low bias and low variance, it means that this is sort of where I'm at relatively lowest possible bias and lowest possible variance. That's sort of where I want to be.
Is bias kind of like your precision of your model?
Precision is both. In order to have precision, I need to have both. This is precision. I mean, yeah. So where it's low variance and high bias, low variance means more precision in where I'm getting my error, but it's I guess less accurate overall. Yeah. So bias means it's systematically inaccurate. In other words, it's always inaccurate. Variance are predictions that are generally inaccurate because they don't generalize outside my data set. The amount of error that I get when I generalize is going to be higher with variance. And so I want to minimize both. And you see this a lot in linear regression, but we'll see this also in other regression models that we cover throughout this class. Final questions on polynomial regression.
How does the out of sample error increase so drastically as the complexity goes up?
Well, it doesn't necessarily always decrease drastically, but you can imagine that in this case it's kind of interesting because I have third order, and you can imagine that if I start increasing, I mean, it's not really going to increase as drastically as it's decreasing over here. So it's not always going to be necessarily symmetrical, but it's almost always going to increase, and it might even like level off. But on average, every time I'm adding a term, I've hindered the ability of my model to generalize. And so when I'm adding more terms, it's going to increase. It's not necessarily going to increase drastically. And this, for instance, in this concrete example we went in class, in this case it increases drastically. But you also have to consider this is a logarithmic scale. So this is only going from 0 to 1. If I took the log off, it's basically reaching a point where it's fitting the model, fitting the training data perfectly, but the test data is just not lining up. And so in this case, it's not always going to increase drastically like this. And you can also imagine, like, if we had sort of a simple model, right? If I were to sort of plot a very basic, sort of keeping the model as simple as possible, or sort of the data set as simple as possible. In this case, there's also fewer samples. So if you get more samples, you get less of a volatility in that change. But if you imagine if I have sort of a simple example like this, right, where my training data set is relatively small, maybe it looks something like this. And if I all of a sudden see, so if I train a model, let's say, this cubic function is a good approximation, and then I make some. So this is degree equals 3. And then I have some, say, like, really complex function like this. And then you're going to see like these wild swings, right? If I have a higher order polynomial, what you're going to see is you see the extreme of this value here where I have these extrema that exist at sort of the boundaries of my polynomial, right? So I have these extremely high swings because there's nothing in between these 2 points. And so these extreme swings at the boundaries, as soon as I start making observations over here, now I have a massive error. Now the error here between my sample is huge. And so that's oftentimes why you see, if you have samples that extend beyond the boundary, you're seeing this spike up here as a result of these large, highly volatile swings in your higher order polynomial. And so you have like these massive gaps are really, in our example in class, are what are causing that cliff. Other questions? Okay. So I want to cover the example, or at least the pre-course homework that we discussed, or that I sent out on Slack yesterday. Before I get into that, I want to sort of set up the premise of logistic regression. So we've covered, I mean, in the domain of learning algorithms, regression is king of its domain when it comes to looking at continuous supervised algorithms. In other words, all the examples we looked at so far had some sort of value, some sort of multi-valued output and multi-valued input. But what happens if we want to look at classification for categorical algorithms? I gave you guys, as part of the pre-course exercise, you were looking at detecting fraud on fraudulent accounts based on sort of two key variables, how much income a person had, and what the amount of balance, what the amount of credit balance in their account was. And you had something look sort of like this, and so as balance, the amount of credit balance increases, and say their income increases, you have a series of points where maybe I'll split circles for saying they don't default. Right, and we'll put sort of like what you saw is something like this. And there's a little bit of overlap. But we were really trying to minimize, we're trying to basically find the separating line between these two data points. And I think you found something like this. And this line should look familiar. It, again, looks something sort of like b to the m x to the m plus sum of the terms, plus b to the 1, x to the 1, etc. And so we're doing regression. But there was a significant difference in how we evaluated our cost function, right? Because, you know, it's a little bit easier to conceptualize the notion of cost function, the notion of residuals and error, when we're plotting a function that exists in 2 dimensions, or sorry, a set of points that exist in 2 dimensions. But with a classification problem, it looks a bit different. It looks a bit weird. And I'll pull that up. But there was one particular graph. I'm going to run through all of these. You got something that looked like this. Yeah, so this is basically the feature space, and we can see there's some relationship between the credit balance that they have, and whether or not they'll default. And you know, if you look at the distributions in the error bars, there's clearly some difference in the distribution between defaulting and non-defaulting counts with respect to the amount of credit that they have outstanding. And part of the exercise actually did a linear regression on these 2 terms. I mean, we can theoretically, mathematically, for all intents and purposes, do a regression on discretely valued outputs. One of the questions here is, what's the problem with doing a regression on this kind of data? Right. So I just assigned. In other words, if they defaulted, that's 1. If they didn't default, that's -1. And you know, just like we've done in all the other exercises in this class, we did a linear regression. But we also talked last class about certain assumptions and certain caveats that linear regression makes. And what assumptions does this type of regression violate?
There's not a lot of variance on
What do you mean by variance?
the negative 1 or 1. There's no.
Yeah, it's discrete. But we've also sort of looked at discrete values before.
I was actually going to say, like, it does, it assumes that the output variable ought to be discrete rather than a long sets, right?
Well, yeah, I mean, I think,
Just continuous.
yeah, but it's also assuming that it's, ranges can be anything. In this case, well, there's a few problems with it, right? So you're right that it's as if, like out here, it's like as if I have like 150% chance that it'll default or something like that. It just increases, and then you can imagine that if I have a value way out here, then it's going to predict like, 2,000% chance of defaulting or whatever. And that conceptually doesn't make sense. But, yeah.
But the values of the residuals should be among the
Yeah. Yeah, and if the values of the residuals here are not going to fit a normal distribution, they're going to be what we call heteroscedastic. They're going to be very heavily skewed. So in other words, the amount of errors, as my input value increases, the error is going to get huge, right? If I start having values up here, they're going to start getting bigger. In fact, it's going to look very weird because the errors here are small and they're reasonably large here. So it doesn't. The whole concept of that we've introduced ourselves of, the whole notion of error. And how we've defined linear regression as a function of error sort of falls apart when we're talking about regressing on these categorical outputs. So what we have, maybe there's a better function, maybe there's a better way of defining this regression. Maybe there's a better function we can use, just as we use polynomial regression to sort of try to find fits in nonlinear relationships in our input and output variables. Maybe there's a function we can use here. And we'll come back to that in a little bit. But in order to understand, like one of the underlying assumptions of really any form of machine learning is maximizing the probability of predicting something that happens. In other words, I want to basically be, at a fundamental level, I want to be able to look at my data, make some inferences, apply a model that finds a relationship or discovers a relationship or describes a relationship between my input and my output data. And with linear regression, that's fairly simple. With classification, though, when we're talking about finding a discrete set of outputs, maybe there's a better way than linear regression. And we'll get into basically the mathematics of this in a little bit, maybe not entirely in this class. But if I tell you, sort of question, if I tell you, maybe I tell you that an ad on a site has a 33% conversion rate, 33.3% conversion rate. And I ask you, what is the probability? What is the probability, given this, that a new user converts? So yeah, customer conversion rate, it's 33%. What are the odds that any new user coming to that website will convert? 50%? Why 50? Yeah, it's sort of counterintuitive, but the conversion rate, the probability, and this is the difference between probability and odds, right? So if I have, that means if it's 33% conversion rate, that means that So one user converts divided by one conversion plus two non-conversions. But if I look at the ratio, the probability of one conversion to of conversions to non-conversions, it's one conversion per two non-conversions. It's 50%. In other words, we did basically, this is, we'll say, the number of positive results over positive results plus the negative results. And we'll call this probability of conversion. And we also defined, maybe it's best to show this visually. When we're talking about probability, what we had over here in this graph, in this example, is we had a set of points here. Draw these along this axis, right? There's some overlap. But we have there's a clear separation here, and this is default. We can sort of think of things in terms of conversion and defaulting. We had defaulting, and we said not defaulting, no defaulting. And our independent variable here was the balance in their account. And we know that for any, we want to predict the probability of their defaulting. The probability of default as a function of basically the account value. And conceptually, you can imagine that if I maybe find some point here, this is maybe the 50, the split point, right? And as I go to the right, the probability of them defaulting is going to increase. I can't definitively say whether they'll default or not. We can't always describe things in terms of certainties. So we have to do our best, and really the means, the language, the protocol for doing our best is maximizing the probability that we make the correct classification. In regression, linear regression, we're trying to minimize the error to maximize the amount of certainty we have. In the classification, it's really the same principle, but we're talking about the probability of making the correct decision. And you can imagine that as I sort of go further to the right here, I'm never going to get above 1, but I might sort of approach 100%. As I go to the left here, I can't always be 100% sure that when they have a lower balance that they won't default. But you can imagine that it's going to probably get lower and lower. And by the way, I guess they technically could have negative, we could have like a debit. But what we get is really a function that looks like this. And we call this, there's actually a particular function that we'll use to describe a relationship between the probability of an outcome. This is our outcome. The default and the not default is a function of some input variable. And this function has a name. We call this a sigmoid function. And it comes up a lot in statistics. call this our sigmoid function. And it's described as mathematically as 1 divided by 1 plus e to the x, where my balance is my x. And there's actually a relationship between logistic regression and linear regression. Because where I said the probability where I said previously there was a probability of an outcome happening or an outcome not happening, we'll say that the probability of event, some probability of some event, has some probability p, and then we'll say the probability that the event didn't happen. Sorry, so I'll put complement. Often use this symbol here for complement of the event not occurring. If it's either one or the other, then it's just 1 minus p, right? So in the case of our conversion, if we were talking about the probability of conversion was p times 1 minus p. And if we say p, we do sort of a transformation of variables, we can say p is equal to maybe e to the x. In other words, if we can basically look at log p, if we look at the logarithm of p, we can define basically the log odds as being, let's say, log of p over 1 minus log of p. Sorry. If we look at this, if we look sort of back in the sigmoid function, we have some 1 over 1 minus e to the x. If we multiply both sides by e to the minus x, we get e to the minus x, e to the minus x, minus e to the minus x times e to the x. This is just going to be e to the minus x over e to the minus x minus 1. And if we take the log of both sides, if I recall correctly, we basically get a relationship between the probability of event happening versus the probability of event not happening as a function of our independent variable x, and we call this our sigmoid function. And we can express it again. What we're seeing here is something that looks very much like the linear regression function. It's just been transformed in space according to some exponential that's bounded between 0 and 1. And the nice thing about this function is that it fits our data points much more nicely. So we have the issue that when we have data points that don't fit, or we try to fit a line to data that's to an outcome that's supposed to be either true or false, we get a very odd distribution in our errors with respect to our data points. We get a lot of heteroscedasticity. We get errors that are non-normal. We get predicted values that are less than or greater than 100%. So it turns out, we have sort of a strategy of dealing with this. We define a cost function in terms of our sigmoid function. I want to review. This was basically addressed. The whole point of this sort of pre-class exercise was to see that. So I'm going to go through this, and we'll go through in more detail, or at least the concepts of logistic regression in more detail next class. But really, you had a data set, and there was, if we look at the data set, if we sort of summarize the data set, there were 3 or 4 independent variables. So if we do, let's see. Just look at the summary. There's basically, the y is the target, default is the target variable, and we have student balance and income. And I only focused on balance and income just to keep things simple. And we basically plotted a few of these, and we visualized, we could, just by exploring the data, we could see that there was a distinction between the defaults and the non-defaults. And as sort of a preliminary step, I equalized the population of the true and false values so that the populations were roughly the same. And that was just sort of increased my accuracy. And then I applied, so in the theme, in the spirit of the previous examples, I applied linear regression, and I did a transformation of variables to find some relationship. And I said that, if they were above some value, then they were going to default. If they were below some value, they would not default. And this is actually very, very similar to what the process is like for logistic regression. And I will take you through the same sort of example, the same sort of workflow for logistic regression. And we'll cover this in more detail next class. But again, we can plot the sigmoid function, and this is, basically we can express this in code, just as we express the sine function and all the other functions. I'm using linspace to define the domain of x, and it's very finely grained to make it look like a continuous curve. You can imagine that, if I took this down, it would, basically just defining a lot of points so that it looks like a continuous function. And then just plotting the sigmoid function. But it's the same data, and by the way, when I call describe, describe will only work on, it'll only print values for numerical attributes. So student, which is one of the attributes, it's not going to describe, because it's a categorical variable, it won't, it's not, you can't really define like a mean and median and so forth. But a lot of this looks familiar from what we did at the beginning of the class on linear regression. So I've just defined, I've converted student to be rather than being true, it was yes or no in the original data set. So I'm just converting these yes and no values to binary values, so I can actually do proper calculations. And then I'm just basically selecting the first few, the features of interest, and I'm calling those x. And remember, we call x, we denote capital X to represent our input variables, and we use y, it's basically defined, I'm storing the target variable as y, and I'm splitting it. This is exactly the same function that we used just about an hour ago, the train test split. I'm splitting my x variable and my y variable, and I'm saying I want to keep 30% of my data to be the test data set, and I'm passing the random state variable. And remember I talked at the beginning of class about shuffling your data and how we want to shuffle our data. The random state value, this is what is called the seed value. So I can set this to be whatever, but as long as this is all the same, it will shuffle it in the same way. Oftentimes when we define random values, they'll have a seed value that is a deterministic value that determines the initial state of the random number generation. So if the random state is always the same, then it will produce the same random number. And sometimes when you see random number generation that you want to be random, it'll be like something like time.milliseconds or whatever. But But random seed is just random state is just the seed value, and so I'll just make a note of that. Random state is just a seed value. So I take train and I convert it back into data frame so I can plot histogram. When I call .hist, just like how we did scatter plots in other examples, we use pd.scatterplot to, scatter matrix. We do pd.scatter matrix to look at, to visualize data sets having continuous inputs. If I do scatter matrix on variables that have discrete outputs, it becomes less clear. So it's a little small, but you can see when I'm doing scatter matrix, it's sort of a waste of space and a waste of time. I'll make this a little larger. Size equals. It's not very insightful because, I mean, I can't look at these discrete variables and really see what the, see distributions here. The distributions are really what's interesting. So in this example, rather than doing a scatter matrix, I just did a histogram. And yeah, you can see that it shows there's a very clear, very heavily skewed distribution, right? So some things to note just right off the bat, looking at this data set. Very, very skewed proportion in terms of students, and also somewhat skewed distribution of accounts very skewed in terms of accounts that will default, somewhat skewed in terms of student populations. So it looks like maybe, I don't know, less than 25% of my, maybe 25% of my total data set are students. Maybe, I don't know, a few percent or so or less are actually defaulting. And so this is always something to note when you have a heavily skewed data set, because it means you'll need to take extra steps, do the weighting. And we're just getting into classification right now, so we're not going to discuss this in this lecture, but it'll be a recurring theme. And yeah, so I'll just plot the continuous variables, income and balance. Interesting that there's sort of a little bit of a, seems to be somewhat of a bimodal distribution in terms of income. So it seems to be like a primary mode, income around 40,000, and there's, I guess, like a lower distribution around between 10 and 30,000. Can label these by, I'll make this a little more transparent, so a little bit of overplotting. But there's clearly a distinct population, there's clearly a relationship between accounts that are defaulting that have a high credit amount, right? Which isn't surprising, but unfortunately it's not mutually exclusive. So there's definitely accounts that are defaulting, and there's definitely accounts that are not defaulting that are sort of in the same space as those that are defaulting. And this is what I mean that we can't always isolate, we can't always be 100% sure, but we can sort of maximize and think of strategies for how we handle those imbalance cases and cases where there's overlapping data. In training the model, really the only difference here, again, I talk about logistic regression is again, just a type of regression. If this is exactly the same as in my previous example, if I replace linear regression with logistic regression, I really have, it's really exactly the same as I did in this exercise. So I did the regression here. The only real difference is that I'm replacing linear regression with the logistic regression. And it's going to return both a coefficient and an intercept. So running that, I get two coefficients. Let's see, linear regression is not defined. So again, the coefficients of my logistic regression are just this beta 1 and beta 0. Logistic regression is basically just taking a similar form of regression, but my cost function, really the fitted model, is just going to fit the form. Y hat is 1 over 1 plus e to the minus. But I have the same function here, so it's going to be beta 1 x1 plus beta 0. And this is the linear case. This is the linear boundary. But you can imagine that I can also, the same principal polynomial expression will apply. I can do 1 plus 1 over e to the minus the v to the m x to the n. I can generalize this to the higher order case in the circumstance where, let's say, I want to have a nonlinear separation of my boundaries. So if I have cases where I say I have a set of points like this, and a set of negative points like this, I might need to define a boundary that fits like this. And again, this function is still a polynomial. We can still apply the same principles that we applied back when we did nonlinear regression, or sorry, polynomial regression. We can still, the same principles apply. We were basically trying to find some higher order fit, and we're applying a cost function. And the cost function is an exponential, but it's still the same notion of cost, the same notion of applying a best fit. It's just that the function, the underlying function that we're using to fit that model is an exponential rather than a linear function. So now I've defined my betas, and I've basically the part is, it's interesting that the step of scikit-learn is actually relatively small in comparison to the rest of the preparation, rest of the visualization. And this just goes back to what I was saying in previous classes, where the pre-model workflow, really, you spend a lot of time processing and cleaning the data. And it takes about at least 70% of your time. The modeling itself, unless you're generating a very complex model, the modeling itself is not terribly complicated. So next step, now that we always sort of define the machine learning workflow in 3 stages: the pre-model workflow, the modeling, and the evaluation. And in this period of in the evaluation here, I'm a little more detailed. I just sort of want to obviate the relationship between our sigmoid function and really the observation that we, the set of observations that we have. So again, I've found beta sub 0 and beta 1 sub x. This is mathematically the same as what I plotted over here. You can imagine that just as I plotted, if I change the sign here, if I multiply by e to the x, sorry, my sign is backwards here, isn't it? So if I have an e to the negative x here, and I change all these to positive, then I get e to the plus x over e to the x plus 1. And that's just this equation here. So it's mathematically expressing the same thing. You see the sigmoid function in both forms. I prefer the e to the minus with the negative coefficient here, just because it's one less term. Sometimes in documentation, you see it like this as well. But I'll sort of highlight this, and we'll call this our sigmoid function. And all we're really doing in logistic regression is finding the parameters beta sub 0 and beta sub 1 in the case where we have, in the simplest case, to define the fit of the sigmoid function. And remember, beta 1 sort of represents the slope of this line. So if I increase beta 1, it's going to increase the slope of this. Beta sub 0 is basically sort of like a bias or a shift. And so just like beta sub 0 in the case of linear regression, define the y-intercept of that slope, beta sub 0 really defines the I guess what we'll call the halfway, the 50% intercept, and where that lies along the x-axis. And the beta 1 defines really like the specificity, in other words, how steep this slope is. So we found this function, and you guys should be able to open this notebook and follow along and be able to run all of this. But if we overlay, if we sort of look at the sigmoid function, and again, I'm plotting really the same data set. The only difference between this data set and the one I went through last class is I'm not undersampling the negative results. So what we saw here, in this case of simplifying and keeping this example simple, I gave it about a 50-50% representation. But you can imagine that if I took that 50% out, we would see a bunch of samples down here that did not default, and that's what we're seeing here. So this is really the same graph that I showed in the pre-class example where we had a line going through it, and this is the fit of the sigmoid function. And again, we can make an observation and we can really define, just as we had the observation, the error between the observation and the linear case was the difference between the point and the model. The error here is just going to be this residual between my observation and the observation, which in this case is 1, and the observation, the sigmoid function, which is probably about 0.9 or so, 0.91. So this is my residual, this is my error, the difference between y and y hat. And I'm trying to find the sigmoid function, the parameters of the sigmoid function that best minimizes that error. It's exactly the same principles as we've applied. It's just that the function itself is a little more weird looking, but from a conceptual standpoint, it's exactly the same. And so if we can evaluate the probability or the error as being each of those values. I want you guys, in the last maybe 10 minutes or so, to work through this example and try to determine the probability, the odds, and the log odds. In other words, the probability is just, again, my y-axis. So if I'm detecting, if I have, say, a value of a balance, if I told you that a person has $2,500 balance on their credit, then you would say, given this model, you would say there's about a 90% chance that they'll default. If I told you that there was a $1,000 balance, you would say that there's maybe a 0.0 whatever probability of default. It's maybe like a 2%, 3% chance, right? And about where they have maybe a 50% chance of defaulting, that's about when they have maybe $1,900, $2,000, there's about a 50% chance of their default. So we call that probability. And we defined, we discussed like the difference between probability and log odds. So if there's, say, if there's a 30% probability, if there's a 50% probability, actually it's 33%. 33.3% probability. We said that the odds of that happening would be 0.33 over 1 minus 33.33, which is about 50%. And I also want you to find what the log of that is. And if you don't have time, that's okay. Focus on these two first. So focus on what the probability is and what the odds are. And then once you find the odds, find the log odds. And if you can't run the notebook, that's okay. Just sort of estimate it from this graph. And I'll hopefully make this larger. Can everyone see this okay? If you can find the exact value, awesome. If not, that's okay too. Oh, and don't forget your exit tickets before you leave. Super important. What's that?
We're on 4.
describe at a high level how it would work for when it's more than just two features.
Yeah, multi-class, yeah, yeah. Yeah, that'll be next class. Yeah.
So you said you don't know yet. This is one of the Python networks. So when I run this cell,
Yeah, that warning is benign. So everyone, so it's kind of fine. So when you apply in the public thing in you want some label for all of the needs to be all the variables, and we need to declare one in that case. So labels are what are used to like generate the legends and things like that. So just letting you know that there's labels.
there are no clocks here, or these.
Those are
things where using obviously an error bar. It's like variables
You know, go over the first try. And then something like that.
Rounded, right?
Yeah, because that looks like good stuff. I'm still confused about all these instances where there's chaining, and I think I had another separate notebook where there was another instance of chaining.
Yeah.
I'm not sure how that.
I mean, that's just letting you know basically that you're modifying copies. In other words, you have some original object, and the copy happens when you are. There's certain chains like what calls like copy dot or like dot head dot something. Chain functions will usually return defensive copy. So that's usually when that's happening. But I can't say that without seeing the example.
No, but there was an example from one of the I don't recall now, I'm not personally, but there's an example, one of the notebooks which had been, which I didn't code. There's some machines.
Sometimes the warnings are benign. I mean, if they're supposed to
Like it'd be that form now too.
Yes.
This is just a more elegant way to do it. Is there always a more elegant way to do it?
There's an more elegant way to do it, except for this one. But I mean, it depends. It's not just because you're getting the error doesn't necessarily mean it's wrong. It's
No,
just
understood
the
what
way
I'm saying, is I don't have the ability to certain and when you get this change, because of what you said in the past, you don't really know, right? Almost ipso facto.
well,
It's causing a problem.
that's true. I mean, it sort of depends on what you're at. Sort of circumstantial.
I'm saying if it's a type 2 error, then it might not recognize it.
But I guess it's also about knowing what the error means, or like why the error is and why the error is. Yeah, it does, which just takes time.
Okay.
Oh yeah, you're Then I was looking for a now I get this. Yeah, but it's here, so it's actually.
So this is all right. So that, yeah, and then I'm thinking of some
Yeah.
changes for right shared so like shared text. And then run this, that puts your text in the model.
Why do we, I don't know, maybe it's not indexing, but why is it, why do we index it, why do we index beta 0 and beta 1? Oh, is it because of the tuple at the end?
So code or you talking about coefficient?
Right here. When we plot these, or even for like the probability odds, you have beta and then beta, is that the 0th index?
Yeah, so beta is always original.
Beta
Remember beta is a vector.
is, okay.
It's not beta 1, beta 0, beta 0. You can imagine that.
Don't we only get 2 betas out of this logistic regression, which I was used to?
But this is beta. Here, it's just P1 equals bounce coefficient.
Wait, this is, yeah, so beta, this is, oh, so you're just saying which one in this, the column? Oh, okay. It's alright.
It's almost with parentheses.
Okay, yeah. So you're just specifying, okay, which beta for the sake of that formula.
Right, exactly. Again, notice the difference in the equation here. So it's basically the same principle behind the regression, it's just applying the uniformity.
Oh, yeah.
Yeah, the NC dot ext is the exponent.
Yeah, okay.
Those PDF that you want to look at.
Yeah.
Do you have a posting on GitHub?
Yeah, I do. I think so. Yeah, I should. This one?
Yes.
Data? Yeah, it's under logistic regression.pdf, and it should be there. Yeah, it's under pre-class. I'll copy it to,
Okay.
yeah.
And even like the previous PowerPoint, they should be somewhere in there.
The logistic regression, or sorry, the polynomial regression.pdf.
Even though the visualization
It is here, yeah. I don't know why it's like this, but
Yes.
yeah, I don't know why it got rotated, but it's there.
Okay, it's up there.
Yeah. I'll post it right now, just to make it more clear.
What is the y-axis for 0 to 18? We also do 0
Well, I think it's taking the inverse of odds. In other words, it's doing 1 over 1 minus p. Sorry, p over p minus it's taking probability times 1 minus the probability. So in other words, I can say like if odds are times 1, that I put in the sense of odds are times 1, that. So yeah, it can be greater. So it's like 99%. So it's like if probability equals 99.99, then 0.99 or 1 minus 0.99. And again, remember that this is really the relationship between the e to the x or the 1 minus e to the x. It's the same thing as 1 over 1 minus multiply both sides by x. See it? Yes. ECX. And this becomes 1. This goes like this.
Minus x times e to the x is 1.
Thank you. Yeah, take care.
And that 1 you have. Alright. Larger than 1.
Yeah. Yeah, because your denominator becomes basically close to 0, and your numerator stays the same.
Okay.
Hold on. You can do it now.
We can do it now?
Yeah.
Okay, yeah.
That stuff is. You guys do a lot of volunteer stuff. Volunteer things. People get very comfortable. Oh, good.
Alright, so, sorry, back on so I think I get this. I guess the question is, so I understand what this is saying. It's like you split your data into 2 sets, by train and then by test, right? You run the regression on by train, and then using that model, run it on by test and see, get the R-squared and see if it's okay, right?
Mhm.
That's what okay, so I get what you're supposed to do. I believe, so hold on. So this is getting like the B sub 0 and B sub 1 for all this stuff, right? Or no?
Yes, that's your coefficient stats. So stats model has a little bit of different API than scikit-learn, but yeah, it'll return your coefficients, yeah.
And then I think I don't know if I did the same thing. Did I do the same thing down here, or is this a little different?
That's exactly the same, yes.
Ish, yes. Okay, cool. That's what I thought too.
Did you get the same coefficients?
Yes, I did.
Yeah.
There we go. So it's the same thing.
Right.
So then I guess the question is for, like, how do you just do the same thing and then like change this to, like, how do I get the test data into this? Because I'm assuming I want to put it here,
Yeah.
right? So would I just literally copy all of this?
Well, wait, so X is, I would always use a convention to separate your X and your Y. So I would use like X underscore train for training data and Y underscore train for training data.
Yep.
Are they facing you? Yeah, I think so. Yeah. Alright, thanks, Anthony.
No problem. See you Thursday.
Yeah.
Okay, so now that I have this, I guess my question is, like, I understand that I need to run that through this. I don't know how exactly. And again, I think it's just, my first guess would just be to like copy this and just change this to test and then run it through.
Well, so I guess there's sort of like 2 things. You fit a line, right? So you have all these points here. And these points we'll call X test.
Okay.
And then what you've done is this line has been, this training example, this line has been evaluated on, this is, I guess, what we'll call Y. And it's been trained on, by definition, this is train. This is, by definition, has been trained on the training data.
Right.
And then what you'll do is you'll calculate the R-squared here.
I don't actually have the Y hat. I just have the pieces that I can use to calculate the Y hat.
You have the Y hat by virtue of the pieces of having, yeah. So in other words, Y hat is...
I'm just saying, like, I don't have a number here that is like a Y hat for any particular point.
So-
I have the pieces where I can figure it out.
So Y hat is never really a number. Y hat is really just like a function, like a relationship
Right.
between. So,
If I have an X, I can put it in, and I need another X, another X, another X.
right. So if you have Y hat, and again, Y hat is just like these coefficients, so it's just whatever this coefficient times all the way to B1 x1 plus beta sub 0. So in other words, you have all the betas. So the betas are your coefficients. This is just coefficient 1, this is coefficient n, etc. And you have all the x values, and this is just x train, right? And this is, I guess, like the 0th index, sorry, the nth index. And this is x train with sub 0. So you have the coefficients. The coefficients are exactly your model. This is really like the kernel, so to speak, the pearl in the oyster of your model, the beta. So when you do the train, so when you say, I guess in stats models, it's lm.fit, then you do lm.co.cof, and there's an underscore. These are the coefficients which are a result of you fitting x. So now you have everything that you need. So now you have the y hat. And the first thing that you have is defining the r squared of the training data. And the r squared of the training data is just, in this case, y. It's just what we described in class, where it's like y times difference of your model, and then you square it. And then you do the sum here, and this is squared, and then there's basically the mean. So you have the y hat remains the same for the training data and the test data.
Right.
So you have a bunch of test data. So let's say that these points represent, you have an r squared, and you've summed up all these residuals, and you've done this calculation to calculate your r squared of your train. And then you come and you say, what's the r squared of the test? And now you have, I think it's 50-50 in this example.
Right.
You have some data points here, and now you do the same thing. Again, the line is the same, but you sum all of these up, and you get r squared on your test data.
Right.
And this is going to be the sum of y train minus the y hat squared all over basically the normalization term, which is the difference, the sum squared total. But the only real different variable here is the
Hey
y
guys.
sub test. Yeah.
Hey, I'm sorry to interrupt. Well, like we're closing right now,
Okay.
so if you guys want to hang out more, you guys can hang out on the 3rd floor, so like 10:15.
Okay.
Okay. Okay, I do get that. I guess the only thing is I don't understand how to put it right that here.
So
Do you know what I mean? And
Yes.
also I don't know what this is, where that came from. I think I had everything else besides that.
So you have your model, but you have all your x's and y's, right? So this is just some point, and then this is just some point, like this is y train, and you use that basically to subtract. So you can evaluate y basically. So y is going to be again just some beta term, some beta sub n. But instead of, in this case, it was x for a test value, this case it's just going to be for a training value, this is going to be it
X
for
test.
test. Yeah.
Yep.
So if you multiply those together, all those terms together, then for any given observation in x, whether it's any given observation here, whether it's a training sample I should say, for any given observation along x, you can find the value of y given y hat. It doesn't matter, it can be anything. It can be any
Yeah.
number that's on your train data, number that's on your test. And then from there, you can basically apply the cost function, the r squared function, on any set of data points, whether it's in training or test. In terms of how to do it, I think you understand it conceptually, but maybe you don't understand how to do it in
Right.
scikit-learn.
That's the problem.
So I could.
Is it in one? It's in one of the notebooks now.
It is in one of the notebooks, and we did also cover it as an
I
example.
did it in class today, right?
Yeah, but it's also in that notebook that we did in class.
Okay, and it's not, and I guess, so the thing, that's what I thought that it was in the class notebook, but I
I think
is
I
that a
posted
difference
that.
between because I felt like the class one was for polynomial,
It's the same.
same thing?
It's
Okay, I was
exactly
like,
the
I
same.
don't know what that
Polynomials,
is yet,
yeah.
I'll find that out tonight. But, okay, cool.
So that's what I was
No problem.
Yeah. I won't be available tomorrow, but
No worries, I mean, that was actually helpful in itself, so I will piece it together.
You'll find they're relatively similar, the R-squared values are relatively similar.
Yeah. How's it going for you?
Good, it's about time with us. Spend like hours preparing each lecture and like rehearsing it and then going back over it.
Oh, rehearsing it